Okay, so we're going to look at a little offshoot of functions now, which is called parametric equations. But first off, we're going to briefly appreciate René Descartes. René Descartes is a French dude. He's the founder of modern philosophy, apparently. He came up with this speech, I think, therefore I am. He invented power notation, so the little things that are on squares and cubes, he came up with that. He was the first person to properly link algebra and graphs, so in a lot of ways, he's to blame for this. More importantly, he invented the Cartesian coordinate system, from his name, Descartes, of using x and y to represent across and up. And specifically, a Cartesian equation is then one that links x and y in some way. So basically every equation that you've ever put into a graph is a Cartesian one. He died of pneumonia, caught while tutoring the Queen of Sweden in a drafty castle. What a guy. Anyway, let's talk parametrics. So the reason to bring that in is that we're going to be talking a lot about Cartesian equations here. I wanted to make extra sure we knew what they were. That's stuff that involves x and y. Because we're going to look at something called a parametric equation, which is a different way of writing stuff that isn't just in terms of x and y. And the idea is to define both of those terms in terms of a third variable, which is normally called t. The reason it's normally called t is because it normally stands for time, because this is very often used in mechanics to describe the vertical and horizontal movement of an object under effect of forces. So you split it into two things that are dependent on time and not on each other. Anyway, here's an example of a parametric equation. We've got x equals 2t and y equals 2 squared. And you can see that we've got a domain defined for our t. These are the possible values that t can actually have. Now our question here is we want to find a Cartesian equation form of this equation. We want it to be y equals something in terms of x. So how could we do that? Well, we know x is equal to 2t and we know y is equal to 2t squared. So first thing we could do is we could rearrange that to be x over 2 equals t. Therefore, y would be equal to t squared, so it's equal to x over 2 all squared. So we could say that y is, I suppose, a quarter x squared. So that's the general idea. We have got away from the t's and we got back to our Cartesian form. Now, the second fact that we need to be aware of is that the domain of a function is the range of pt, because pt defines the x values, and the range of f of x is the range of qt, because q in this case defines the y values. So what are the domain and range of our function? Well, let's do them one at a time. So the domain would be the range of what we're defining x as of 2t, for t being between 3 and minus 3. Now if you think about 2t, that's just a straight line graph. So between minus 3 and 3, it's just going to go from minus 3, minus 6, up to 3, 6. So our domain is therefore going to be that x can be anywhere between minus 6 and 6. Our range would be the range of what we're using to define the y values, which is t squared. And again, if we think about that between t is minus 3 and 3, we would get part of a quadratic function that would start at minus 3, 9 and would end at 3, 9. If you think about the range of that, it goes up from 0 to 9. So our range would be that y is between and including 0 up to 9. So that's our answer for that second part. It says to sketch the curve now. So you can sketch it by subbing in different values of t, but we're actually going to leave that for a later lesson. We're going to use the Cartesian equation form today. So we've changed it to being y equals a quarter x squared, so we're just going to sketch that. We know, let's draw that again. We know that our x values go from minus 6 to 6 because we found the domain, and we know our y values go from 0 to 9, so we know this maxes out at 9. And there you go. That's a parametric equation that we immediately turned into a Cartesian equation and then did some stuff with. So we're going to spend a bit of time looking at a few different examples of parametrics and how we can combine them and do things with them. So here's a different one. We've got here x is ln of t plus 3, and we've got y is 1 over t plus 5, and t is greater than minus 2. We want to come up with a Cartesian form that links these two things together, and we want to define the domain of the function. So when we say x is greater than k and find k, we want to find its domain. So in our first example, what we did was we sort of redefined one of the expressions in terms of t and subbed it into the other one. And we can do the same thing here. So let's take the x expression. We've got x is equal to ln of t plus 3. If we want to get rid of ln, we're going to have to do e to the power of x, is equal to t plus 3. That'll get rid of our natural log. And then we can subtract our 3. So if we want to form a Cartesian equation, we know that y is equal to 1 over t plus 5, so we can sub that in there and get that it's equal to 1 over e to the x minus 3 plus 5. Now we probably want to simplify this because we don't want minus 3 plus 5 next to each other. This is just overall 1 over e to the x plus 2. Now, does that have to look pretty? No, that's our Cartesian equation. We're told that our domain is that x is greater than k, and we know that the domain is equal to the range of the function that we use to generate x. So it's going to be the range of x equals ln of t plus 3 for t greater than minus 2. Now the ln graph, it's going to be shifted 3 to the left, looks something like that. And if t equals minus 2, then x is equal to ln of minus 2 plus 3. It's equal to ln1 is equal to 0. So our minimum value would have to be 0, and our greatest value is kind of unbounded. So our value of k is simply that x is greater than 0. Now the second part of the question wants you to find the range of fx. So if we want to find the range, then we need to find the range of the y function. So we want the range of our y function, which is 1 over t plus 5. And again, we're saying that t has to be bigger than minus 2. Now 1 over t plus 5, again it's going to be shifted to the left, would be a reciprocal graph, looking something like that. If we want t is greater than minus 2, then we're going to start at a third. So let's think about this. If we say t is minus 2, then we're going to read off that value as being a third, because we can sub that into 1 over t plus 5. And it obviously just gets lower than that, but never crosses 0. So our overall range is going to have to be that y is certainly less than a third. That's the biggest it can be, but it's also greater than 0. Now I'd always recommend trying to put these in the calculators to check them. There is actually also a parametric setting on calculators that we'll have to have a look at when we come back, but you're more than welcome to have a little look there, see if you can figure it out. Something else to bear in mind is that we can have some trig shortcuts when we're doing our Cartesian things. So just as a reminder, those are the trig, shortcuts that you should be familiar with. We've got these three, which are kind of all offshoots of sine squared plus cos squared equals 1, and then we've got our double angle formulas. None of these are given to you in the formula book. You need to make sure that you know them. So here we've got x is sine t plus 2 and y is cos t minus 3, and we want to find a Cartesian equation. And we're going to, in this case, use the very top equation that sine squared plus cos squared equals 1, because I can see that this involves a sine and a cos. And I know that's the only way that I can combine those two together. So here's what we're going to do. We're going to rearrange that first equation to be x minus 2 is equal to sine t. We're going to rearrange that second equation to be y plus 3 equals cos t. Then we're going to square them. So we're going to say this is x minus 2 squared is equal to sine squared of t. Square them both, so y plus 3 squared is equal to cos squared of t. and then we've got sine squared and cos squared, and we know that those two things add together to give 1. So sine squared t plus cos squared t equals 1, then so does x minus 2 all squared plus y plus 3 all squared equal 1. Okay, so that's the first part of our question. That's our Cartesian equation. T is all possible values, so we don't need to think about range and domain. So our second part of this question is to sketch it. Now, what equation have we just come up with here? This is the equation of a circle. Remember, a circle is x minus a all squared plus y minus b all squared equals r squared. So this must be a circle. The center of the circle would be 2 minus 3, and the radius would be 1, because that's the square root of 1. So sketching it, 2 minus 3, maybe we'll put that over here. Radius is 1, so it's not going to reach either of the axes. It's going to be a little circle based at that point. Cool. Okay, so again, we obviously got our list of trig identities. Which one do you think might be relevant here, given we've got a sine t and we've got a sine 2t? Did you say this one? I hope you did, because that's what we're going to use. So this one obviously is the only way we've got of linking sine 2t with sine t, so we're going to make some use of that. So we can start off by saying that y is equal to 2 sine t cos t. And replacing sine t is obviously fine, that's just x, because, well, it is. But what about cos t? Well, we can kind of use the top equation as well. So we know that sine squared t plus cos squared t are equal to 1. We know that sine squared t is equal to x squared, because sine t is equal to sine t is equal to x. And then we know that we can rearrange this to be that cos squared t just on its own is 1 minus x squared. We can square root that, and we can say that cos t is the square root of 1 minus x squared, and we can plug that into the equation. So we know that x equals sine t, and we know that cos t equals the square root of 1 minus x squared. So overall, our Cartesian equation would be 2x, because that's what sine t is, times the square root of 1 minus x squared. And then we have a Cartesian equation, y equals something in terms of x. Now we want to find its range. And remember that the range of the function is going to be equal to the range of the y parameter. It's going to be equal to the range of sine 2t between minus pi over 2 and pi over 2. So what does that look like? Well, sine 2t is the same as the sine graph, but kind of compressed a little bit. So the sine graph looks something like this. And that would normally be between minus pi and pi, but because it's sine 2t, it's compressed together, it's between minus pi over 2 and pi over 2. So what's the range of this function that we've drawn? Well, it's anywhere between minus 1 and 1. So our answer for this question, its range, is going to be that y could be anywhere from minus 1 to 1. Okay, so here's another trig shortcut. I think it's our third one and our final one. Again, here's our list of trig identities. Which one do you think is relevant? That's right, it's the cot squared and cosec squared, because this has got cot and cosec and nothing else does. So, according to this, we know that cot, so let's rearrange this first. So let's say that x minus 2 is equal to cot t, and y plus 2 is equal to cosec squared of t. Okay, what we want to do is to put that into this top equation. So the top equation says that cot squared, let's say t, plus 1 is equal to cosec squared of t. And then we can substitute those two expressions into here. So we can say x minus 2 squared plus 1 is equal to y plus 2. Not y plus 2 squared, because y plus 2 is actually equal to cosec squared. We're basically done at that stage, aren't we? We can just make this y equals by simply subtracting the 2. So we'll have y is equal to x minus 2 all squared minus 1. And Well, I think we'll just leave it like that. We don't need to make that any more expansive than it is. I might rearrange it to have y in front. That's purely for aesthetic reasons. So there's my answer to the Cartesian equation of the curve. Second thing we need to do is we need to find its domain. So again, we need to remember this. If we want the domain of a parametric equation, that's equal to the range of its x function. It's equal to the range of cot t plus 2 for t between 0 and pi. So again, you'll have to sort of sketch that out. We're going from 0 to pi, and the cot function can be quite hard to remember. So what I tend to do is draw out the tan graph first, and between 0 and pi, tan graph just looks like that. And then you kind of just reflect it. So when it's high, cot is low and vice versa. So our cot graph looks something like that between those two values. It's cot t plus 2 though, so it would be 2 higher than that. So the actual graph would sort of bend at 2, not at 0, and then come back down. But it kind of doesn't matter because it still covers all possible values. So our domain must be all possible values as well. Okay, it says lastly that we need to sketch this curve. So I'm just going to rub this graph out of the way. There we go. So the reason that I didn't want to change it from here is this is a complete the square form of a quadratic. And more specifically, it's a complete the square form which tells us the minimum point of the graph is going to be 2 minus 1. And it also tells us it's going to be a positive quadratic. So 2 across, minus 1 down. This is going to be the base of our graph. We know it's a positive quadratic. I guess by the time we get to 1, this will be 1 squared minus 1, so it'll cross over at 0 and 0 at 1 and 3. But we don't tend to need to know that for a sketch. That would be enough. So yeah, positive quadratic with a minimum point of 2 minus 1.